Welcome everyone. I'm excited to kick off today's presentation on air conditioning. We'll be diving into the basics of inverters and how they play a crucial role in modern cooling systems. This first slide is just the beginning. We'll explore what makes inverters so efficient, how they work, and why they're a smart choice for your air conditioning needs. Let's get started. Let's take a closer look at the basics of an inverter. First, consider the average voltage, VAV. When VAV is not equal to 0, it indicates that there is a net voltage over time, which is typical in AC signals. Now, if VAV equals 0, that means the positive and negative parts of the waveform cancel each other out, resulting in no net voltage. This is characteristic of alternating current, where the voltage changes polarity periodically. In the case of DC or direct current, we see no voltage changes at all. The voltage remains constant over time, which is why DC sources like batteries provide a steady voltage. When we look at a graph of voltage versus time, for DC, the line stays flat, no fluctuation. On the other hand, AC, or alternating current, involves voltage that varies positively and negatively over time. This is what we see as the sinusoidal wave, plus and minus voltage changes that occur periodically. So, to connect these ideas, DC has no voltage changes over time, making VAV equal to the voltage level itself, while AC involves continuous voltage variations, with the average over time potentially being 0. Understanding this difference is fundamental when working with inverters, because they are devices that convert DC into AC power. Let's take a closer look at how we can change the compressor's rotational speed by adjusting its frequency. On this slide, you'll see the formula N equals 120 times F divided by P here. N represents the number of motor rotations, F is the frequency, and P is the number of poles. What this formula tells us is that the rotational speed of the motor is directly related to the frequency of the power supply. By increasing or decreasing the frequency, we can control how fast the motor spins. For example, if we set the frequency to 70 Hz, the motor will rotate faster compared to when we set it to 50 Hz. You can see in the graphs here how the voltage U varies with time t for each frequency setting. This ability to change frequency gives us a lot of flexibility in controlling the compressor's operation, making it more efficient and adaptable to different working conditions. It's a key concept in modern motor control and energy management. Let's take a closer look at some key concepts related to power conversion. First, we have the inverse transformation, which involves changing direct current, or DC, into alternating current, or AC. This process is essential when we need to supply AC power from DC sources like batteries or solar panels. Next, there's rectifying, which is the opposite process, converting AC back into DC. Rectifiers are commonly used in power supplies to provide a steady DC output from an AC source. Then we have inverters. An inverter is a device that takes DC and converts it into AC, often used in renewable energy systems or uninterruptible power supplies. Conversely, a rectifier circuit converts AC to DC, which is crucial in many electronic devices. Understanding these circuits is fundamental because they play a vital role in how we manage and convert electrical energy, seamlessly integrating different power sources into our systems. Let's take a closer look at this diagram. On the left, we have the DC side, which stands for direct current, and on the right, the AC side, or alternating current. The symbols with the plus and minus signs indicate the polarity of the voltage. What's important here is the direction of the current flow, which is shown by the arrows. The key concept is how an AC to DC rectifier works. It takes the alternating current, which changes direction periodically, and converts it into a steady DC output. You can see that the AC input goes into the rectifier, which then produces a unidirectional DC output. The example illustrates this process clearly. Essentially, the rectifier allows current to flow only in one direction, effectively converting AC into DC. This is a fundamental part of power supply systems, especially for devices that require a stable, direct current. Understanding this conversion process is crucial for grasping how power supplies and many electronic devices operate efficiently. Let's take a closer look at this example of an AC to DC rectifier. On the left, you see the AC input, which has both positive and negative cycles. The AC waveform alternates polarity, as shown by the plus and minus signs. The goal here is to convert this alternating current into a steady direct current, which is what we see on the right as the out. The rectifier essentially allows current to pass in only one direction, blocking the negative part of the cycle. This is why the output is a pulsating DC signal, with the positive peaks remaining while the negative parts are eliminated. Understanding this conversion process is fundamental because many electronic devices require a stable DC supply, even when they are powered from an AC source. This example clearly illustrates the basic operation of a simple AC to DC rectifier, which is a key component in power supply design. All right, let's take a closer look at this example of an AC to DC rectifier in action. On the left side of the slide, you see the waveforms labeled T, S, and U, V. The T, S represents time in seconds, and the U, V shows the voltage over time. This is the AC input signal, which naturally fluctuates between positive and negative values. Now, on the right side, we see the resulting waveform after rectification. While the AC waveform swings both above and below zero, the rectified output only stays positive, effectively converting AC into DC. This process is fundamental in power supplies, as it allows us to transform alternating current into a steady direct current. The key point here is that the rectifier removes the negative parts of the AC wave, resulting in a unidirectional voltage. This example clearly illustrates how, with proper circuitry, we can take an AC signal and produce a DC output suitable for most electronic devices. Remember, this conversion is essential for powering our gadgets and systems reliably. Now let's look at how we can use a capacitor to smooth the DC output. As you can see on the slide, the graph shows the voltage across the capacitor, U, over time, T when the rectifier converts AC to DC. The output isn't perfectly steady. It fluctuates, creating ripples. The key idea here is that by adding a capacitor, we can reduce these ripples and get a more stable voltage. The capacitor charges up when the voltage rises and discharges when it drops, effectively filling in the dips in the voltage wave. This process results in a smoother, more consistent DC voltage, which is crucial for powering sensitive electronic components. So, in essence, a capacitor acts like a reservoir, holding energy during peaks and releasing it during troughs, ensuring the voltage stays as steady as possible. This step is vital in power supply design because it improves the quality of the output, making sure our devices run reliably and efficiently. All right, let's take a closer look at this example of a DC to AC inverter. As you can see here, the diagram illustrates how the inverter converts direct current, or DC, into alternating current, or AC. The symbols with the plus and minus signs on the DC side represent the positive and negative voltage sources. When we switch these on and off in a specific sequence, the inverter produces an alternating waveform. The out part of the diagram highlights the AC output, which is what we use to power most household appliances and industrial equipment. This process involves switching the DC voltage at high frequencies, creating a waveform that mimics the AC power supply. Overall, this example underscores how inverters are essential in systems like solar power setups, where they transform the stored DC energy into usable AC power. It's a fundamental component that bridges the gap between energy generation and practical use. All right, let's take a closer look at this example of a DC to AC inverter. On the left side, we see the input, labeled in, which is direct current, or DC. This is the type of electrical power you get from batteries or solar panels. Moving to the right, we have the output, labeled out, which is alternating current, or AC. This is what most of our household appliances use. The key point here is that the inverter's job is to take this steady DC input and convert it into an AC output that can be used in standard electrical systems. You'll notice the symbols with plus and minus signs on the DC side, indicating polarity, and the wave symbol on the AC side, representing the alternating nature of the current. This conversion process is crucial because it allows us to power AC devices from a DC source, bridging the gap between different types of electrical systems. Think of it as a translator, taking the energy from a battery and making it compatible with the electrical grid or appliances. Understanding this example helps reinforce the overall theme of how power conversion technologies enable us to efficiently use renewable energy sources and improve energy flexibility. It's a fundamental concept that underpins many modern electrical systems and innovations. All right, let's take a closer look at this example of a DC to AC inverter. Here, you can see the input side, labeled in, which is where we supply the direct current. The plus and minus signs indicate the polarity of the input voltage. On the output side, labeled out, we see the alternating current with its positive and negative cycles. The key point here is that the inverter's job is to convert the DC input into an AC output, which is essential for many applications, like powering household appliances or feeding energy into the grid. This example highlights the basic flow. Direct current enters, the inverter switches it rapidly, and then produces an alternating current that can be used by AC-powered devices. It's a fundamental component in many renewable energy systems, especially solar power, where solar panels generate DC and we need AC for most home appliances. So, understanding this simple diagram helps us grasp the core function of all inverters in energy systems. Let's take a closer look at this example of a DC to AC inverter. On the left, you see the frequency, labeled as F in Hz, and on the right, the voltage, U in volts. The key idea here is that by changing the switch speed, which essentially controls how quickly the inverter switches on and off, we can alter the frequency of the output AC signal. As you can see in the graphs, when we adjust the switch speed, the time period T in seconds also changes. This variation in the switching rate results in a different frequency of the output AC power. The main takeaway is that by controlling the switch speed, we can effectively convert a DC supply into an AC output with a desired frequency. This process is fundamental in many power electronics applications because it allows us to generate AC signals from DC sources, which is crucial for powering AC devices or feeding electricity into the grid. So, the overall result here is a simple yet powerful way to perform DC to AC conversion by manipulating the switching frequency. Let's take a closer look at pulse width modulation, or PWM as it's often called. Essentially, PWM is a technique used to improve the way we manage alternating current, or AC. By adjusting the width of the pulses in a signal, we can control the power delivered to a device more efficiently. This method allows us to simulate different voltage levels without needing complex transformers or variable resistors. What's really important here is that PWM helps us achieve smoother and more precise control over AC power, which is crucial in many applications like motor speed control or lighting. It's a way of making the power delivery more adaptable and efficient, aligning perfectly with our overall goal of optimizing electrical systems. So, in essence, pulse width modulation is a clever technique that enhances how we handle AC power, making systems more flexible, efficient, and responsive to different needs. All right, let's take a closer look at slide 14. Here, we're exploring the core components involved in power conversion for air conditioning systems. First, you'll notice the terms out and in. These refer to the flow of electrical energy from the source to the load. On the left, we have the DC to AC inverter with PWM, or pulse width modulation. This is a key technology because it allows us to efficiently convert direct current into alternating current, which is essential for controlling the compressor and fan motors smoothly. The PWM technique is especially important because it helps us adjust the output voltage and frequency precisely, improving energy efficiency and system performance. On the right, there's the AC to DC rectifier with smoothing. This component converts AC power from the mains into DC power, which can then be used or stored. The smoothing part is crucial because it filters out the ripples and fluctuations, providing a stable DC supply. This stability is vital for the inverter to operate effectively. Overall, these components form the backbone of modern inverter-driven air conditioning systems. They enable us to control the compressor and fans more precisely, leading to better energy efficiency, quieter operation, and improved comfort. Connecting these points back to our overall theme, it's clear how advances in power electronics are transforming HVAC technology for the better. Let's take a closer look at the overview of the different phases involved in power conversion. We start with PWM, which stands for pulse width modulation, a technique used to control voltage and current in power electronics. The AC VAR, HZ, indicates variable frequency AC, which is essential in applications like motor speed control. Next, we see AC Vari, HZ again, emphasizing the importance of frequency variation in AC signals. Moving on, we have smooth DC, representing a steady direct current output, which is crucial for many electronic devices that require stable power. Following that, we encounter DC at 50 Hz, referring to a specific frequency component within the DC conversion process. Sometimes we need to incorporate AC characteristics into the DC output for certain applications. Then, there's AC at 50 Hz, which is the standard mains frequency in many regions, highlighting the importance of matching the power source to the load. Overall, this slide provides a snapshot of the different phases and types of power signals we encounter, illustrating how each plays a vital role in the overall power conversion process and ensuring our systems operate efficiently and reliably. All right, let's take a closer look at this slide. We start with the output, which is 240 volts AC, and notice that the frequency can vary depending on the application. Moving to the input side, it's also 240 volts AC, but here, the frequency is fixed at 50 Hz. This is typical for many standard power systems. Now, this entire setup involves a few key components. First, we have the compressor, which is what actually does the work in many systems. Then, we have the inverter, which uses pulse width modulation or PWM to convert the DC into AC. This is crucial because it allows us to control the voltage and frequency more precisely. Before the inverter, there's a rectifier, which takes AC and converts it into DC. This DC is what the inverter then modifies to produce the AC output. So, to recap, the process involves converting AC to DC via the rectifier, then using the inverter to generate the desired AC output, with adjustable frequency and voltage. This setup is fundamental for controlling equipment like compressors in various applications, providing flexibility and efficiency in power management. Let's take a closer look at slide 17, which explains what an inverter is and how it functions within the system. Starting with the question, what's an inverter? An inverter is a device that converts direct current, or DC, into alternating current, or AC. This is essential for controlling motors and other equipment that operate on AC power. Now, the slide introduces some key components and concepts. PFC, or power factor correction, is important because it improves the efficiency of power usage by reducing reactive power. The IC, or integrated circuit, plays a central role in controlling the inverter's operation. When we see the symbols for W, V, and U, those represent the phases of the motor or the system's power lines, specifically three-phase power, which is common in industrial applications. The 3-phi indicates three-phase power supply, which provides a more stable and efficient power delivery. The comp refers to the compensation circuitry that helps maintain stable operation of the motor under varying conditions. The motor itself is driven by the inverter power module, which supplies the necessary power and control signals. Additionally, the inverter system includes an active filter, which helps reduce harmonics and electrical noise, ensuring cleaner power output. Driving frequency, or driving freak, is a key variable because it controls the speed of the motor. As the frequency varies, so does the motor's speed, which is crucial for precise control. Temperature difference, or temp, diff, is also tracked to monitor thermal conditions, helping prevent overheating and ensuring reliable operation. The graph on the right illustrates how temperature differences are categorized based on the operating frequency, with higher frequencies generally leading to higher temperatures, over 250 degrees C in some cases, indicating the importance of thermal management. Finally, the overall block diagram of the inverter system ties all these components together, showing how they interact to control motor operation efficiently and reliably. Remember, understanding these components and their functions helps us see how the inverter system manages power, controls motor speed, and maintains system stability under different operating conditions. So, one of the key benefits of an inverter air conditioner is its ability to deliver quick and powerful cooling or heating. When we look at indoor temperature regulation, inverter units are designed to respond faster compared to conventional non-inverter models. For example, with an inverter system, the cooling or heating process is about 15% faster. That means you'll feel comfortable much sooner after turning it on. Unlike traditional units that might take longer to reach the desired temperature, inverter air conditioners adjust their compressor speed continuously. This is where the switch-on time becomes important. Instead of repeatedly turning the compressor on and off like in conventional systems, the inverter maintains a steady operation, which helps it reach the set temperature quickly and efficiently. So, what does this mean for you? It's simple. An inverter air conditioner can cool or heat your space faster, providing a more comfortable environment in less time, and ultimately saving energy by maintaining that temperature more consistently. This is a clear advantage that ties into the overall theme of efficiency and performance in modern climate control technology. So here we see the temperature settings and how the inverter system helps maintain a consistent indoor climate. When the temperature is set to 0, 5 or 1, the inverter adjusts its operation to keep the room at that desired temperature. Unlike conventional non-inverter units, which turn on and off repeatedly, the inverter smoothly modulates its compressor speed. This means that instead of constantly stopping and starting, the inverter keeps the compressor running at a steady, optimal level. As a result, the indoor temperature stays more even and comfortable. You won't experience those sudden fluctuations or the feeling of the room getting too cold or too warm. This is a clear benefit of inverter air conditioners. They provide a more stable environment and improved comfort. Plus, because the compressor operates more efficiently, it also saves energy over time. So, the key takeaway here is that inverter technology helps maintain a consistent temperature, making your space more comfortable and energy efficient. So, here on this slide, we see that using an inverter air conditioner can save you around 44% per year on energy costs. That's a significant amount that adds up over time. Unlike conventional systems, inverters adjust their compressor speed based on the indoor temperature, which allows for more precise control. When the room reaches the desired temperature, the inverter reduces power, keeping the temperature steady without turning on and off constantly. This contrasts with conventional units, which switch the compressor fully on or off, leading to more energy consumption and temperature fluctuations. The key benefit here is saving money by using less energy. Plus, with the inverter, you get a more comfortable indoor environment because the temperature stays consistent. So the main takeaway is that choosing an inverter air conditioner not only cuts down your energy bills, but also enhances your comfort. It's a smart, efficient choice that aligns perfectly with our goal of sustainable and cost-effective living. Now, let's take a look at how noise levels differ between models. As you can see, the inverter model operates at around 50 decibels, while the conventional model is a bit louder at 52 decibels. Interestingly, some inverter models can even go down to 48 decibels, which is noticeably quieter. So, what does this mean for us? One of the key benefits of an inverter air conditioner is lower noise. This means a more peaceful environment, especially during nighttime or when you need to focus. In essence, choosing an inverter model not only helps save energy, but also reduces noise, making your living space more comfortable. This is a great example of how inverter technology enhances overall user experience, aligning with our goal of better, smarter cooling solutions.